This is the video for section 7.1 in Math 1050. So in this next chapter, in chapter 7, we're going to talk about some geometry. So it's called analytical geometry. And in particular, we're going to talk about conic sections. And this first one, we're going to be doing the ellipse. So briefly, analytical geometry is the study of geometry using the tools of algebra and using a coordinate system. Midpoint, distance, all these things will come in, formula, parallel, perpendicular, intersecting lines, all these algebraic things mixed in with the geometry, right? So in particular, we're talking about conic sections. So conic comes from cone, and you all probably know what a cone is. But in mathematics, a cone is two cones tip to tip, right? A double napped cone, they call it. So these are the four conic sections. So a conic section means that it's a cross section of a cone. And we've already talked about circles, so we'll briefly review them, but mainly we're going to talk about ellipses, hyperbolas, and parabolas. And in this section, we talk about ellipses. As you can see here, the green is the plane that's cutting through the cone, and that cross section is what that shape is. And sure enough, this last one, which will be the last one that we study, is the parabola. And we have talked about parabolas before. We're going to talk about them in a little bit different way. The hyperbola is the only one that has two separate parts to it. And the ellipse and the circle are kind of related. The circle is kind of a degenerate form of the ellipse, I guess you might call it. So if you remember the circle, we have this equation, x minus h squared plus y minus k squared equals r squared, and hk was the center. And hk is going to continue to be the center, or in the case of the parabola, the vertex. It's just a nice way for us to denote the center, and it kind of stands for the shift, as we talked about transformations. And remember that the circle, we talked about the circle as being a set of points. So in math, we call it a locus of points, but it's that set of points that all meet this certain criteria. The criteria in a circle is that the distance from a certain point is always the same, and that distance is called the radius, right? And that certain point is the center. Well, the ellipse has some of these same things. See, the ellipse is like a elongated circle. It's used in a lot of fields. So the definition, if we talk about this locus of points again, it's the set of all points such that the sum of the distances to two different fixed points is always the same. So in a circle, we had one point, right, called the center, but you might think about it as a focus. It's like that place, that center, right, that focus of the circle. Well, here we have two, and so plural for focus is foci. Now, I know it says here that it's pronounced foci, and sometimes it is pronounced foci. Great Britain pronounces it foci, and I took a Latin class a few years ago, and they don't even have a soft C sound. So in Latin, you would definitely pronounce it foci. So I will be pronouncing it foci. If you want to pronounce it foci, I'm going to know what you mean, so it will be fine. So, and this is saying that that distance that distance from the focus to the point on the circle and then to the other focus is always going to be the same. All right, and so no matter where I draw it, if I go from the one foci to the ellipse and then back to the other foci, that sum of those two distances is always going to be the same. And we're not going to take the time to derive the formula here, the equation, but we would do it with the distance formula. I'll just show you the equation. If you want to see it sometime, then let me know and I'll try to record one. But you can probably look it up and find it as well if you wanted to see it. So an ellipse can be elongated in any direction. But in this class, we're only going to do horizontally elongated or vertically elongated. So these are the two. First one is horizontal. The second one is elongated, is vertical. And the thing that you're looking at is the long length, the longest length. So from one tip to the other in the longest spot is called the major axis. And that is like the important line. It has 5 important points on it. There are 2 vertices, there are 2 foci, and there's the center. All of them fall on the major axis. And so that's what we are looking at when we decide this one is going horizontally, this one is going vertically. So you might think that there are 4 vertices. There are not. So these are called vertices. Oops. These are called vertices. Jeez, what is going on? Where the minor axis crosses, we don't call them vertices. Sometimes we refer to them as the minor vertices, and that would be okay because it's clear. But if it just says vertices, we're talking about the ones on the major axis. Quite often, the way you're going to have the other ones pointed out to you would be the endpoints of the minor axis. I think, though, in a little bit here, I think I refer to them as the minor vertices because that was quicker to write. All right, so we have the major axis. The center divides the major axis in half, right? And that makes it twice that length from the center to the vertex. You got that same distance twice, right? And then the other one, the shorter one that's perpendicular and goes through the center, that is the minor axis. All right, so here is a little closer, bigger view. So the major axis again goes the long ways, and if we were going vertical, then tip this whole thing on its side, and it would be the same, right? Because when we change it to be vertical, then the longest side is going up and down. So the longest side is always the major axis. So it doesn't matter whether it's going back and forth or up and down. The longest axis is the major axis. And that's the axis, that's where the foci are found, and the center is there, and the vertices are there. Okay, so let's just look at some of the details of the equation and how we find some of these things. Okay, so this is the equation, and there's one little difference between the horizontal one, the one that would be going back and forth, right? So the horizontal one is going to be in this direction and the vertical one is going to be in this direction, right? So there's there's one difference between these two equations. So see if you can see what it is. So hopefully you saw that the a squared and the b squared were flipped. Well, a is the distance from the center to a vertex. And let's look at where that was. This is a, the distance from the center to a vertex, right? Well, this is also a, the center from a center to the vertex. Sorry, it should be right on that blue line. That's a, and a is bigger than b because it doesn't matter whether we go up or down or back and forth. The longest one, it has the vertex, and so the longest one is always a, and b is the shorter one. All right, so when we look here, a is the bigger number. A is the bigger number, and it's under the x. And what that tells you is that that major axis, the one with a, that is parallel to the x-axis. Whereas in this one, the a, the bigger number, is under the y. And so that's telling you that the bigger number, or the major axis, is parallel to the y-axis. So that's how you tell from the equation whether it's going to be horizontal or vertical. So the graphs will look like this, and you notice that we're allowing h and k to be our center. And sure enough, when you look up here, there's h, x minus h, just like we did with circles, right? And x minus h doesn't change just because it changed back and forth, right? And there's the k, y minus k. So it's telling us that the center of the ellipse is going to be the opposite of whatever that shift is inside that x minus h and the squared, right? And we'll look at some examples. It'll probably be clearer after we look at some examples. Okay, so the center is hk on both of them. H always goes with the x, and k always goes with the y. So let's look at this blown up a little bit here. So B and C here form a right angle, and if I connected B and C, it turns out that that's the same as A. So A is this length here, but A is also that length there. And the way we know that is because that the two of them together has to always be the same, and it turns out that it's always 2A. Because if you think about this one where it's laying flat, it would go all the way over there, which is 2. From here, it would be everything except for this little bit here, but then we're going to go back to the vertex, to the foci, and that would be it again, right? So it's always going to be 2A. So this very middle one, where it's right there at the minor axis, each one is A. And so this is a little right triangle with A here, and B here, and C here. So using the Pythagorean theorem, we got A, B, and C mixed up, so don't do it in the way that you always do the Pythagorean theorem. This is B squared plus C squared equals A squared. And you know that A is the biggest, because A is obviously bigger than B, because that's how we define which one's A and which one's B. And A is bigger than C because C is on the major axis but not at the end, right? So A is definitely the biggest, so A is going to be the hypotenuse since it's a right triangle, right? So we know that that is true, then we can actually find C given A and B. So knowing that A and B are from our equation, we can always find C by using this relationship here. All right, so now when we're trying to find the foci, remember that the foci are on this axis here. And so if the foci are on this axis, that means it has the same y value as the center. And so do the vertices, right? So that's why the y is going to be the same as the y in our center, because they're on a flat line, they're on a horizontal line. But from the center, we're gonna add C and subtract C, right? So that's why I take whatever the center, the x value of the center, I'm going to add the C, and that gives me my new x value. I'm going to subtract the C, and that gives me my other new x value for the other foci. So when we are going vertically, then as you can see down here, we start at the center. Oh dear. We start at the center, and we're going up C, right? So the x value is the same, but then we change the y value to go up or down, depending on which one we want, right? So in this one, the x value stays the same, but the y, we take the k, we add C to the k, or we subtract C to the k to give us our two different foci, right? And the vertex is going to be the very same when it's horizontal. So remember that the distance from the center to the vertex is A, so we're going to take the y value will be the same on all this whole horizontal line, right? This y value will be the same, but we're going to take the x value and add A and subtract A, and that's how we get the x and the y. The y is just the same as the k, but on the vertical one, it's the x that stays the same, and then it's the k that we add A to and subtract A from. So the endpoints of the minor axis just kind of flip to the other way. Remember, it's going the other way. It's coming up. So this time the x is the same. So h stays the same. The x value stays the same as the center. But the y value goes up and down by b. And in the vertical one, it's the y value that stays the same because it's now this horizontal one. And it's the x value that goes back and forth by b. So hopefully it'll make more sense as we start doing some problems. So here is our first problem. And we're going to just find all these things out about it and then graph it. All right, so the first thing we want to look at is this going to be a horizontal major axis or a vertical major axis? And you tell by where A is and where B is, or A squared and B squared, right? So the biggest one is A, and the biggest one here is under the x, so it is going to be parallel to the x-axis, so that will be horizontal. Okay, so that means it's going to look like this. It's elongated horizontally back and forth. All right, so the center, remember that's the HK. And so that is found by these 2 points, right? And it's the opposite because it's x minus the center. So the center is going to be -3 and 1. And so I could actually start graphing it here. I'm going to go -3 and up 1, and there's my center. All right, so now let's just look at what A, B, and C are. Remember, A squared was the bigger one, so we have A squared is 16, so A is 4. And B squared is 9, so B is 3. And then we have to look at that Pythagorean relationship, right? Remember that A squared was the biggest one, so it's A squared equals B squared plus C squared. Or you could write it as C squared, it's a C, not an E, equals A squared minus B squared. And the only reason that that's more handy is because I have A squared and B squared right here, right? I got 16 minus 9, which is 7. So C squared equals 7. So C is the square root of 7. Okay, so, all right, so now let's look at the vertices. So I can easily graph this because from my center point, I've got a horizontal line to get to my vertices. So my y values are all going to be the same as my center. So it's going to end in 1, right? Those are going to be my y values. My x values are going to take -3 plus 4, which will be 1, because I'm going to go from -3 over 1, 2, 3, 4. And -3 minus 4, so it's going to be -7. So that'll be right there. The minor vertices, or the endpoints of the minor axis, they're going to go the other way. My x value is going to be the same as the center because it's a vertical line. We're going up and down. But now I'm going to take the 1 plus 3 because that's my b, right? So 1 plus 3 is 4, and 1 minus 3 is -2. So I'm going to go up 3 and down 3, right? So I have enough at this point. I could sketch the graph, but let's find the foci while we're at it so we can put those on there. Give myself a little more room. So remember that the foci are on this major axis, and so they have the same y value as the center and the vertices, so they end in 1. Right? But now we don't have quite as nice a number. And I know some of you will want to plug it in your calculator and get an approximation, but it's just fine to leave it exact and to say it's going to be -3 plus square root of 7 and -3 minus square root of 7. So square root of 7 is bigger than 2 and less than 3. So it's between 2 and 3, right? So from this -3, I'm going to go up not all the way to 0, right? So it's going to be somewhere in here. And I'm going to go down to somewhere in here. Now, here's what my ellipse looks like. So try not to make it totally look like a football. The ends are kind of curved. It's more like a rugby ball, you could maybe say sometimes. But that's what it looks like from our equation, okay? So, oh my, where's my equation? Whoops. It did not work. Well, that's not very nice. Okay, so that equation is number 2 on your sheet. So it should be 4x squared plus y squared minus 16 equals 0. Let me just make sure it's not in the next one. Yeah. Okay, that's the one. All right, so do you notice what's the problem? This equation is not in the standard form, so I can't pick out a and b from this equation. So I need to change it to the standard form. So if you remember what that standard form looked like from a couple screens back, it's equal to 1. So that is a good place to start, to put all the numbers on the other side so we can start getting it equal to 1. All right, so I will rewrite this as 4x squared plus y squared equals 16. And now I can divide by 16 to make it equal 1. Okay, so the standard equation is x squared over 4 plus y squared over 16 equals 1. All right, so let's go through these now. So you try to answer the question before I answer it. See if you can get it right and see about y, right? So is this horizontal or vertical? So if you remember, the bigger number tells us, right, the one that it's under. So the bigger number is 16, so that's under the y squared. And so it's horizontal, or it's parallel to the y-axis, which means it's vertical, right? That means it's looking like this. It's going up and down. All right, and what's the center here? Because this doesn't look quite like our equation we did, but what is the center? What does that mean? Well, there's no x minus a number inside that square, right? Or y minus a number, so that means there's nothing subtracted. There's no shifted. So it's just 0, 0. All right, so A is the square root of the bigger number. So A would be the square root of 16, which is 4. And B would be the square root of 2. And then to find C, we've got the A squared minus B squared. So I got 16 minus 4, which is 12. So C is the square root of 12. All right, so let's graph what we have so far. We have the center. We know it's going up and down, so if I go up 4 and down 4, that's my A. That gives me my vertices, right? And if I go over 2 the other direction and negative 2, those give me my minor axis. And that's what the graph looks like. Sorry, that could have been better. All right, so now let's just finish the actual vertices and the other points. So we could read it off the graph, but if we didn't have the graph yet, remember it's a vertical line, so x is going to be the same as our center. And that's true for the foci too. Okay, now for the y value, that's where we go up and down, right? So we go up 4 and down 4. And on the foci, we're going to go up the square root of 12 and down the square root of 12. Now I know you could reduce the square root of 12 to 2 times square root of 3, but square root of 12 is kind of nice for estimating, so it's bigger than 3 because that would be square root of 9, and it's less than 4, so it's somewhere in between here, the 3 and the 4. So we actually have a thing called eccentricity, which tells us how the shape is. And we always do C over A. That's the eccentricity, C over A. And so there might be some problems in the homework that ask you about eccentricity. And it's just basically C over A. So it's be square root of 12 over 4. And the closer that is to 1, the more narrow and elongated it is. And the closer that number gets to 0, the more rounder it is. All right, so here's another one, and this is really not in our standard form. But you may remember from when we did circles that we would sometimes have an equation like this. And we needed to complete the squares, about 2 squares, right? The x's and the y's. So if we put our x's together, I got these 2 x's, the 25x squared and the 100, and I'm just going to factor out the 25 since I know I'm going to be kind of short on space here. Okay, and then I've got my y, so I've got 16y squared. I'm going to factor that out of the 96 and the 16. Okay, so 16 goes into 96 6 times. And then I will put the 156 on the other side. 156. Okay, so the number that goes in here, we take half of the 4, which is 2, and we square it, so that's a 4. But really, we've done 25 times 4, so that's 100. So I have to add 100 to this side. So now I'm up to 256. And then in this one, I take half of this -6 and I square it. So 3 squared is 9. But really, I've done 16 times 9, which is 144. So if we add these up, I get 300, 400. All right, so this is going to be, I'm going to have to take up some of this. So 25 x plus 2 squared plus 16 y minus 3 squared equals 144, which I will divide by 144. And then simplify. So not 144. I'm so sorry. 144 was only part of it. It added up to 400. Okay, so here's our final equation in the standard form. Wow. So 25 goes into 400 16 times, and which would mean that 16 goes in 25 times. Okay, so is it horizontal or vertical? And tell me, and how do you know, right? Think about it. Horizontal or vertical? I hope you said vertical. It's because the 25, the bigger number, is under the y, so it's parallel to the y-axis. Right, the center is negative 2, 3. So the a was the bigger one, so 25, square root of 25 is 5. Square root of 16 is 4. And if I have 25 minus 16, that's going to be 9, so square root of that is 3. That's nice. We got nice numbers for all of them, right? All right, so let's do some of this graphing. So negative 2, 3. We're going up and down, and we're going to go up 5. I'm going to a little bit off our graph. And we'll go down 5. And we'll go over 4. And over 4. And the foci are going to be at 3. Oh, I drew that wrong. All right, so there's our ellipse. Now let's get the actual figures. So we know that since it's a vertical line, all the x's are the same in the vertices and the foci. So now I take the y value, which is 3, I'm going to add 5 and subtract 5. And for the foci, I'm going to take the 3 and I'm going to add 3 and subtract 3. So when I find the minor ones, then it's the y value that stays the same because those are going horizontal. And so it would be negative 2 plus 4, which is 2, and negative 2 minus 4, which is negative 6. And that is that one. Okay, I think this might be the last one that we're going to practice on. So I want you to pause the video and see if you can do the whole thing by yourself. Then come back and I'll work it out for you so you can see if you had mistakes or if you had problems with it. So go ahead and pause the video. Okay, hopefully you got it. If you notice, when you want to put this into the standard form, so we don't have any other x's, so that one's done. So 16x squared, that's done. I don't have to complete the square for that. So then I have these two. I'm going to factor out a 9. I'll put the negative 81 on the other side. So this is going to be 25, because half of 10 is 5, and 5 squared is 25. And if we have 25 times 9, that's 225. All right, so let's see, that's going to be 144. I divide everything by 144. All right, so we have x squared over 9. Oops, yeah, that's right, plus y plus 5 squared, and 9 into 144 is 16 equals 1. All right, so if you had trouble getting that far, then pause again and see if you can finish it now. So, is it vertical or horizontal? Well, the bigger number's under the y, so it's vertical again. It's going up and down. The center, so the x is not shifted at all, so the x center is going to be at 0, and the y will be at -5. So 0, 1, 2, 3, 4, 5, it's right there. A is the bigger number, so a squared is 16, so a is going to be 4. B is going to be 3. And so C will be, C squared is 16 minus 9, which is 7, so C is the square root of 7. So we're going up and down, so from -5, we're going to go up 4 and down 4. And we're going to go back over 3 and 3 the other way, right? So there's my graph. So my vertices, the x value is the same as the center point. The y goes from -5 plus 4, which is -1, and -5 minus 4, which is -9. The minor vertices, it's the y value that is the same as the center. So that's going to be -5. And then I have 0 plus 3 and 0 minus 3. And the foci are on that vertical axis, so the x part is the same. And then we have -5. And this is where we just leave it as an exact answer, unless you want to graph it, and you can get an approximation if you want. Oh, sorry, that should have been minus square root of 7. So square root of 7 is a little bit less than 3. So on my graph, I'd go up 2 and some, right? So it'd be less than 3. Those would be my foci. Okay, let's talk about these foci. So we go to a lot of trouble to find them, and we don't really need them to graph, but they are important for things that are used, right? So ellipses are used in a lot of sciences, like in reflections, reflection of light, reflection of sound waves. We'll talk about it in a minute with some light reflections and sound wave reflections. In medicine, they actually use an elliptical machine, and they generate some shock waves at one foci, and the other foci is focused on, it's sitting right at a patient's body where a kidney stone or gallstone is. And so all those shock waves are sent out from one focus and land on the other one. And there's a picture of that little machine there. There's just a kind of cool use of an ellipse. Lots of different things, okay? And buildings, they have, there's a planetarium. There's actually, in the orbits, the orbits of the planets are elliptical. They originally thought they were circles, but they're not. They're elliptical. There's buildings that are formed with an ellipsoid, so it's a building that's in the shape of an ellipse. And so I don't know if any of you have been in the Tabernacle in downtown Salt Lake, and that is an elliptical building. And it said, so what happens at the foci is they call it a whisper gallery when it's elliptical. And if someone stands at one focus point, then and they whisper, at all, you can hear it at the other because the sound waves hit that ellipse and reflect down to the other focus. Right, so it's said that John Quincy Adams put his desk right at one of the focal points, and then he could eavesdrop on people having conversations at the other one. St. Paul's Cathedral is a whisper gallery, and well, I won't forget that one. Let's do this last problem. It's one of the story problems. It's like a story problem in the book. That there are some of these. And when you do these story problems, the work isn't that hard because we set it up in the easiest way possible, right? So we're taking like the cross section of the room and we're setting it up. It's this ellipse. We're setting it up on the axis. That's the easiest one, right? So it's centered at 0, 0. So the equation is just x squared over a squared plus y squared over b squared equals 1, right? And so what they're asking us, or they're telling us that it's 50 feet long. So if it's 50 feet long and the center is at 0, 0, then this point would be at 25, 0. And this point would be at negative 25, 0. Now the other one, it says it's a semi-minor axis. That means it's only half, right? But that's because we're only using half of the ellipse. So this right here, this point right here, is at 12. And so this is telling us that A is equal to 25 and that B is equal to 12. So what they're saying is that if you place a light at one focus, all the light's going to kind of gather at the other focus, and we want to put a statue there so that the light's all going to kind of illuminate that statue. And so we want to know about where to put the light and the statue, so we need to know where the foci are in this. Well, the foci is C. We have A and B, and we need C. And we know that C squared is equal to A squared minus B squared, right? So we have A squared would be 25 squared, or that's going to be 625. And we subtract off the B squared, which is 144. And see, I thought I had that written down somewhere here. Is that 481 or something like that? 481. And so the square root of 481 is about 21.9. As approximately, I should use approximately. So that means that we want the distance from the center of the room to the light as about 22 feet, right? Or 3 feet from the edge, that we could say it either way, right? It's 3 feet from the wall, 22 feet about from the center of the room, and the statue would be the same, 22 feet the other way. All right, so those are ellipses and a few of the ways that we use ellipses. Thanks. We'll see you in class.